think of our logo? Good. Okay, anyone who can explain the significance? Erwin knows. You know the Sheldon Glashow version, right? Yes, so excellent. I'm glad that was not lost on this audience. So this is a group of around now 35, 40 people with expertise in all of these different areas. So people working on simulations of accretion disks around individual black holes, people working on resolved studies of supernova explosions in the ISM, people working on cosmological simulations, the whole gamut. And I think this is what's really needed to try to make progress on this problem. And so our goal is to back away from these phenomenological, observationally tuned subgrid recipes and adopt a completely different approach, which is to base each subgrid recipe on a simulation of the physics on that scale where the process is actually happening, and then to build a ladder of scales up to the scales where we can actually implement this in a cosmological simulation. And I'm sure, because I've already had some conversations about this today, I am 100% sure that it will not work. We will not reproduce the stellar mass function of galaxies and its evolution back to redshift 10 nearly as beautifully as what I just showed you. And we're just going to have to deal with that. We won't throw away our old models, right? We can keep on using those. But within SMAUG at least, and I think within the broader community, we feel like this is the right way forward.
Why are you so sure it will work?
Ask me that again at the end if I haven't touched on that. We already have some pretty strong indications that it won't work, at least based on the work we've done so far. So those of you who are Tolkien fans might remember that Smaug's very favorite special treasure was the Arkenstone. So again, having a good name is just so important. Matthew and a postdoc at the CCA, Drummond Fielding, came up with the name Project Arkenstone, which is very much at the core of the work that we're doing within SMAUG right now. And so the goal of Project Arkenstone is to develop a new subgrid treatment of stellar-driven winds writ large, right, and the circumgalactic medium, because of course stellar-driven winds mix with the circumgalactic medium, to represent sort of this full cycle of wind launching and recoupling and potentially of precipitation of cold material out of the CGM. Okay, so the idea is to sort of have this cycle, and to base these recipes, this new approach, on these very high resolution idealized simulations of the relevant physical processes. So the foundation of our wind launching model is this tool set of simulations called Tigris, another animal, which was developed by Yves Oestreicher and Chang-Gu Kim, who was a postdoc at CCA and is now at Princeton. So these are what are sometimes called tall box simulations of the interstellar medium. So it's like a kiloparsec high in a vertically stratified shearing box, and then like half a kiloparsec wide. You can see here in this little animation the density, the temperature, and the magnetic field strength in one of these boxes. This is run with the code Athena. It's now being ported over to Athena++. And the benefit of this approach is that we can resolve the Sadoff-Taylor phase of individual supernova explosions and try to understand how they actually drive these large-scale winds. So you can see from the movie that these do produce a nice multi-phase wind. There's a very broad range of temperatures from 100 up to 10 to the 6 for the gas. And it also includes OB runaways, so supernovae don't necessarily explode in the dense birth clouds where they're born. They can sort of move out Okay, so many of this past work with resolved ISM simulations have focused on solar neighborhood initial conditions. So one of the big challenges we faced in SMAUG was to try to we sort of had a circular problem. Well, we need to know the initial conditions for these small-scale simulations, but we don't know, in a cosmological context, we don't know what those initial conditions should be. So we've used our existing simulations, like illustrious TNG, to try to get a guess, at least, for the relevant parameters that go into these resolved simulations, like the density of stars, the density of dark matter, the density of gas, the shear, etc. So we've done an initial suite of these tall boxes representing different conditions within a Milky Way-like galaxy. So these range from average gas surface densities of about 75 solar masses per square parsec in the middle, out to about 2.5 in the outer parts. You'll maybe see some of these symbols that say LG, and these just have, essentially you can think of it as having a lower gravitational field from the stars and the dark matter, but the same everything else. So there's an incredibly rich set of data that come out of these simulations. Here it's very boiled down, and it's very boiled down with a view to how do we implement this within the cosmological simulations. So some of the essential quantities we need are the mass loading of the winds, the momentum loading, the energy loading, and the metal loading. And we've extracted this for, we can do this for the whole PDF of gas temperatures, but for now we just drew a line. We said, let's look at this for cold gas and hot gas. So you can see that if you just treated gas all as, one thing, that having one mass loading factor does not make any sense, right? So the cold material is very mass loaded. Oh, sorry, I should have said this is the surface density of star formation plotted on the x-axis. The plots look almost identical if I plot on the x-axis sigma gas, or the midplane density, or midplane pressure, or the gravitational weight at the midplane. These are all highly correlated in these simulations. Whether or not they are in a cosmological simulation remains to be seen. So you can see that the cold material is highly mass loaded, the hot material is highly energy loaded, and much of the metals are actually carried out by the cold material. And similarly, we can look at velocities. This is another important parameter we need to implement the recipes in our cosmological simulations. So here's the velocities for the cold material and the hot material. Much of the cold material doesn't reach a high velocity, and so it's going to fall back, whereas the hot material can reach escape velocity. And again, these are showing medians. Of course, we can measure the full PDF for the velocity of the gas, and eventually we may try sort of sampling from that velocity PDF. So again, now instead of putting in a mass loading factor or a velocity that scales with halo mass or some global property, which is commonly done currently, it's going to depend on a local property. So the density of gas, or whatever we decide to put in on whatever scale you can resolve in your simulation. And Erwin, this is part of why I think that it won't work, because we know what mass loading factors we need to fit the stellar mass function, and they're a lot higher than this. We know that we need a strong dependence of mass loading factor on something like halo mass. We're not seeing that strong dependence so far, so that's a hint that maybe there's something else going on, right? There's no cosmic rays, who knows?
So are you there for halo mass, or it seemed that you were just changing position within a particular galaxy?
Yeah, so we have not yet varied the halo mass. We've varied the local gravity, and there doesn't seem to be a strong effect, but I agree. We obviously need to do a much broader suite of these kinds of simulations before we can conclude anything about the dependence on halo mass. So initially, we plan to implement this within a Milky Way mass cosmological simulation. That's the first step. You have to start somewhere. So then for this other piece, now this material goes out into the CGM. How does it recouple with the CGM? And then what's the fate of that material in the circumgalactic medium. Well, this is also a very strongly multiscale and complex process, which is certainly not resolved in any cosmological simulations. And so again, we need to have sort of this set of nested idealized simulations to try to understand processes such as turbulent mixing in these radiative mixing layers, and then be able to coarse grain those physical processes and include them in our model. So Drummond Fielding has been taking the lead on doing a study of idealized simulations of radiative mixing. This shows temperature, density, Mach number, cooling time, velocity, etc. Again, this is just to give you a flavor that we can measure from these simulations an effective turbulent diffusivity for how this material mixes that we can then include in a diffusion equation that's coarse-grained. Okay, so that's the beginning of Project Arkenstone. Another piece of the SMOG initial projects is to see whether we can develop semi-analytic models as a tool to emulate hydrodynamic simulations. Or put another way, many of the ingredient in the semi-analytic models that we still use today go back to rather, sort of arbitrary guesses that, many of which go back to papers from the late 80s and early 90s, and have never been tested against modern hydrodynamic simulations. So Viraj Pandya